learned the concept of loading effect, error and least count. Now it is time for us to work out some problems, because these concepts are very important in the field of measurements. So we know the loading effect is equal to loading effect given by the ratio EO by EO dash is equal to 1 over 1 plus ZO by ZI. This is what we have learned under loading effect. So if at all we are interested to find out the loading effect, we are supposed to know these two values, the impedance, output impedance as well as input impedance. Unless we know this, we cannot find out loading effect in the measurements. So let us work out one or two problems, or let us see one or two important circuits in finding out what is ZO of the circuit, so that we can select suitable instrument which will have 10 times ZO as the impedance. That is our idea. So for example, let us consider this following circuit. R1, there is a battery source, and R2, another resistance R2, and R3 across, and R4, and it goes to the terminal A, across which we are going to measure the voltage. Here another battery source, and B. Now the problem here is, we want to measure the voltage across AB. There are two battery sources, and so many resistors are connected in this circuit. Now we want to connect a voltmeter, yeah. And what should be the resistance of this voltmeter, we have to find out. For this, unless we know the resistance of the circuit as reflected across AB, we cannot select the instrument. So that is, so to say, RAB, that is our ZO. ZO is here RAB. ZO is equal to RAB. Here it is purely resistance circuit. As seen from AB, what is the resistance of this? So how to find out? That is what we are going to learn. In such circuits, it is better we find part by part. So call these points CD, these 2 points, and across CD, suppose this right hand side doesn't exist, and across CD, what is the reflected resistance of the circuit across CD? That is R1, R2, R3. For this purpose, we normally use a thumb rule. Start from one point C, try to reach the point D, and how many paths are there? So many parallel paths. Then find out the equal resistance of the parallel paths. So from now, if you call RCD, 1 by RCD is equal to 1 by 2 parallel paths. So 1 by R3 is one path. The other parallel path is R1 plus R2, so 1 by R1 plus R2. So now from here RCD is equal to R3 into R1 plus R2 divided by R1 plus R2 plus R3. So simply we say parallel paths of two resistances RA, RB. So RAB is equal to RA into RB by RA plus RB. That is formula. That is what we have used here, finding the equivalent resistance of two parallel paths. Now as well I can forget this now. Instead of the whole circuit, I simply write this RCD. R3 I can write it RCD, because its equivalent value I have put here. The whole circuit is put as RCD, whose resistance is so much. Now you can come, now it is simpler circuit. Now from A to B, how much it will, how many paths you have got? One path is, this is the resistance R5. So from A to B, one path is through R5, another path is R4, RCD, and this for that equivalent circuit we always short circuit the battery source. So we short circuit this. So now here again we have got two parallel paths. So RAB is equal to R5 into the other parallel paths, that is R4 plus RCD, that's all, RCD divided by R4 plus R5 plus RCD. So RCD you can substitute, so that we can have always the RAB in terms of the given resistances. So RAB is equal to our ZO. So this we can find out from these given values, and then 10 times this we select as the voltmeter resistance. So, that is how we find out the existing circuit, the output resistance of the existing circuit. Yeah. Having learned this process, now we have to apply to the conventional circuits which are often used in mechanical measurements. One of the important circuit is bridge circuit, because bridge circuits we are using for converting the resistance change into a voltage change. So, let us consider the following bridge circuit. This is second problem. This is problem 1, problem 2. We are just working out few problems so that the concepts of loading effect and error and least count are clear. So, I will consider the following circuit, bridge circuit. So, this is the excitation. I will call this A. I will start here from A and this B, C, D, 4 corners. Across AC the voltage output is obtained. Okay, it is voltage output is there. So, 2 corners, opposite corners for excitation and the other 2 corners for output signal. Now, here we should know what is the reflected resistance across AC, because here only we have to connect the instrument is to be connected here. So, when you want to select an instrument, what is the resistance, output resistance of this bridge circuit, that should be known, otherwise we cannot select the instrument. So, to say RAC should be known. So, call this point, now let us draw the equivalent circuit. For drawing the for finding out the output resistance, normally we short circuit the battery source. Now, as we have done earlier, these are the 2 points A and C. Across AC we have to find out. So, start from one point and try to reach the other point. How many paths is there? So many parallel paths, and find the equivalent resistance. That is the way we are going to adopt. Now, starting from A, I can go to B or D through, say I will call this I will call this R1, R2, R3, R4. These are the 4 resistances. So, to reach C, I have to start from A. So, through R4 or R3, I can reach the point B or D. And since it is already short circuited, the battery source, B and D remains the same potential or same point. Having come to BD, either through R3 or R4, then again to reach C, from BD I can come either through R1 or through R2. So, to say, I start from point A and I got 2 paths. One path is R3, another path is R4 to reach the point BD, B comma D. Having reached BD, then to reach C, again I have 2 paths, that is R1 and R2, and this is our C. That is how we draw the equivalent circuit by using Thevenin theorem, that is short circuiting the battery source. We start from A, reach C. Now, if we find out the equivalent resistance of this circuit, which is easier, we know what is the resistance across AC. So, to say, now we can write it starting with A, point A. This equivalent resistance is, I can draw one, that is R3, R4 by R3 plus R4. That is the resistance of this parallel path. We have reached the BD, and now this resistance equal to R1 R2 divided by R1 plus R2. We have reached this point C. So, now total resistance RAC is equal to R3, or I will write this first, R1 R2 by R1 plus R2 plus R3 R4 by R3 plus R4. Now, this is the equivalent resistance of the bridge circuits across AC, where we are going to connect our voltmeter, voltage output, voltmeter we are going to connect. In the normal practice, you find R1 is equal to R2 is equal to R3 is equal to R4 is equal to R. In strain gauge applications, we normally purchase 4 strain gauges of 120 ohm, and their bridge is made up like that. So, we will call R1 to R4 is equal to R. In this situation, RAC is equal to R squared by 2R plus R squared by 2R. So, this is equal to, so R of, so we have got R by 2 is equal to R. So RAC is equal to R. It is simple to remember. Suppose the 4 arms of the bridge is made up of equal resistances, then the output resistance of the bridge is same as the resistance of one of the 4 arms. Suppose if it is equal to 120 ohm, each one is made up of 120 ohm, then RAC also will be equal to 120 ohm. That's how we remember. Whatever be the strain gauges that is made use of, for all the 4 bridges, and that will be the resistance of one of them will be, because all of them equal, will be the equivalent resistance of the bridge circuit. So here it will be R is equal to 120 ohm. Now once we know the resistance of the bridge circuit as reflected across AC, then the voltmeter should be having at least 1200 ohm. That is what we have learned. At least 10 times the resistance of the meter should be at least 10 times the existing resistance or output resistance of the circuit. Now the second important circuit is potentiometer transducer, which is often used in mechanical measurements. That is, it is a transducer, that is it is used to sense or transduce a displacement. Probably it is it's a displacement from this, displacement of x into a corresponding voltage, say EO. That is a displacement xi. This is the output voltage. This is the potentiometer which has got where there is its own excitation voltage. This whole voltage is proportionately distributed along the resistance, and when we move this contact up and down, proportionately we have got a voltage output. So if so many millimeter of motion is equal to so many volt, we get it here. That is how we transduce a displacement into a corresponding voltage. Now suppose we want to connect a voltmeter here, then naturally we should know how the output resistance of this existing circuit varies. Accordingly we can select the resistance of the voltmeter. Now we have to see how it varies, the output resistance varies. For that you call this resistance up to this point from here, from A at some operating point, call it as B, this as C, A, B, C. Now we want to connect the voltmeter across CD. Same principle we use it to find out the equivalent resistance. That is, from C to D we have to reach in the existing circuit. How many paths are there? One path is through B to A. B to A I will call Rx, and then if you call this whole resistance is Rp. Rp is the resistance of the potentiometer. Then the resistance from B to C is Rp minus Rx. The whole resistance is divided in 2 parts. One is Rx and the remaining part is Rp minus. Rp is the potentiometer resistance. So here we find equivalent resistance RCD is equal to, now you have got 2 paths, one through this, another through the other one, because we are short circuiting this battery source. So one path is through Rx, so Rx, the other path is Rp minus Rx divided by Rp minus Rx plus Rx, so giving rise to Rp alone, Rp. So this is the equivalent resistance of this potentiometer circuit across CD. Now what is the property of this RCD? Now as we vary Xi, the input displacement, Rx is varying. So you find since Rx is varying, RCD is going to vary. So in selecting this voltmeter, you have to see what is the maximum value it can have. Maximum it can have Rp. So naturally you go for 10 times Rp. But anyhow, it is now suppose if it is varying between 2 intermediate points, then for the particular application we are supposed to find out the variation of the RCD, and accordingly you have to select it. But the main point to note here is, in a potentiometer transducer, where the potentiometer circuit is used for transducing a displacement to voltage, we have got a varying output resistance. This is the important point. Hence we find the loading effect also will be varying one. That is sufficient now to know about this circuit. Later on, when we take out some problem, you will find how to use this varying loading effect properly to how to when there is a varying loading effect, how to make measurements, that you will see little later. We will go to the other circuit. Now it is the another circuit what we often used in measurements is amplifier. Now the amplifier has got some unique property. See what we have learned so far, the circuits, the first circuit some random circuit I have picked up, and second circuit pertain to bridge circuit, the third circuit is for the potentiometer transducer. They are all having constant output, constant or little varying output resistance. It is a unit having a given output resistance. In 2-3 cases it is constant, otherwise it is varying. But here is a unit, then amplifier, which normally an amplifier interposed between. How the amplifier is made use of, we got the transducer where we give our input signal, and then normally we will have this power amplifier, this amplifier, or we can also call it power amplifier, power amplifier. So where we inject power, then it goes to some other actuating, probably this may be a recorder. They consider this is instrumentation. Now we find it as power amplifier has to be matched on both the sides. See, before power amplifier you got one unit, and after power amplifier another unit. So this is a instance where it should possess two important characteristics. When it is looked from transducer, it should it gives certain ZI. It should possess certain ZI, and when it is seen from recorder, it should possess certain ZO. Now what should be the values of ZI and ZO? Now ZI should be very large compared to transducer output resistance or impedance, and ZO should be very small, so that we can select 10 times ZO for a recorder. That means the amplifier is supposed to possess two characteristics simultaneously. That is, ZI should be large for this power amplifier. At same time, the R, or I will say transducer, I consider two terminals. Here also I consider two terminals, which is the actual case. So the when the amplifier is seen across the terminals A and B, it should possess, the circuit should possess a large value, that is ZI should be very large. And similarly, if I consider the 2 points C and D, output points of the amplifier, when the amplifier circuit is seen from C and D, it should possess a smaller value, or ZO should be small, and here ZI should be very large. This is the characteristic what is required, that inherently it is there in the amplifier circuit. For that, I take one simple amplifier circuit and demonstrate it is there, high ZI is there, at same time low ZO is there. For this one simple transistor circuit I will take it. So it is like this, or I will draw the other side. This is the base, point A and point B with the positive, since it comes here. So this is your output point. Output point is C and D. And AB is the input terminals for the amplifier. You should remember the earlier diagram. This AB is the input terminal, and CD are the output terminals of the power amplifier, which you have earlier interposed in the existing circuit. Now we see what is the value of RAB or ZAB, and then Z or ZCD or output impedance, or here it is purely resistance. What are the resistance values? RO and RI and RO, that is RAB and RCD. Now say we will follow the same principle. So this is call it R. Same principle. Let us try to, this is a transistor, this is an emitter, and then this is collector terminal. These are the base, collector and emitter terminals. And we know in transistor circuit construction, between emitter and collector there is a insulating layer, and between collector and base there is a insulating layer, between base and emitter there is also insulating layer. Yeah, that is base is the middle, and it is somewhat like this. Base is the middle, this is base, and this is emitter. This is a construction of a transistor. This is the collector portion of it, and we have the insulating layer here. These are the insulating layer between base and emitter, insulating layer, base and collector insulating layer. So these are two layers are there. So each one is separate, and we say this R junction. Yeah, R junction, between these two junctions, there it's a large value. R junction is large one, is large compared to R value. R is of the order of say about 100 ohm, 100 or 200 ohm, like that. Compared to that, the junction or the insulating layer between these three compartments are large. That is what we are supposed to know in the transistor circuit. Now we find out what is the resistance RAB. From RA up to go to R to A to B, we can go first to base and then through emitter, base to emitter, and come back to point B. This is our input voltage for this power amplifier, and this output voltage. So that is one through the R junction, we will call R junction. So RAB is equal to R junction, I will say R junction, or 1 by RAB is equal to 1 by R junction resistance, R junction, and another one is through base to collector, another R junction is there. So then we can come through R and then to the here and then back to this, we can short circuit. That means plus 1 by one R junction is there between base and collector, R junction plus R. And when we compare R to R junction, this may be neglected. So we find RAB is equal to R junction divided by 2. When R junction is large, so RAB will be moderately a large value. RAB, that is our input resistance, Ri. Ri is a relatively large value. And now we see what is the resistance output for this power amplifier. Again we use the same principle. So RCD is equal to, we go through 1 by RCD, let us put. So we have got now collector to base, collector to base. Collector to base is again we have got one junction, collector to base, and then from base to emitter another junction. There are two junctions, yeah, 1 by twice R junction. Yeah, from C to D we have got two junctions and then come to D. And another path is you can go through this and take the path through R, and this we are short circuiting, come back here, come to D, that is plus 1 by R. So now we find when this value is very large, twice R junction, then this will be too small compared to, because R is small value, 1 by R will be a larger one. So you will find RCD is approximately equal to R. Now R is of the 100 ohm, so 100 ohm for example. So you find RCD is equal to RO. Output resistance is smaller one, whereas RA is a larger one made up of junction resistance. That is how we see an amplifier possess simultaneously a higher input resistance, so that it can be connected to transducer. It may have 10 times resistance already, 10 times resistance of the transducer to connect it, and it has got lower output resistance, so that 10 times the smaller resistance can be the input resistance for the recorder. So it possesses both the characteristics. Yeah. So now it is we will see how to how this loading effect can be made use of in measurements. This is what we will see. We take this first problem. So problem on a strain gauge bridge, say problem 1. There is a strain gauge bridge, where that RO with RO is equal to output resistance as 120 ohm. That means that this strain gauge bridge is made up of 4 ohms, each ohm being 120 ohm. So output resistance of the bridge circuit we have learnt already, it is 120 ohm. Now this bridge, for reading the output voltage of this bridge, there are two possibilities. One possibility is an oscilloscope, oscilloscope of resistance of 1 into 10 to the power 6 ohm. There is one possibility. Another possibility is oscillograph of 26 ohm. This is instrumentation. Once strain gauge, the bridge is bridge output is read with an oscilloscope, or in another instance it is read by an oscillograph where it is recorded. Question is, what is the loading effect in these two cases? It is simple here because RO is given. This actually is Ri, say in the first case, and this is Ri in the second case. And use this formula, loading effect is equal to EO by EO dash is equal to 1 over 1 plus. So you take the first case, RO here is 120, and Ri is equal to 1 into 10 to the power 6. Now this is too large a number, 10 to the power 6 compared to 120, so this will be near about 0. So you will find actually its value is it's about 1 only. 120 or 10 to the power 6 is negligible, so it is near about 1. So in case of oscilloscope, we find since the input resistance is much larger than the output resistance, 10 to the power 6 means near about 10 to the power 4 or 10,000 times or somewhere like that. We want only 10 times, it is much more than this. So in such instances we should see the loading effect is negligible. That is what is demonstrated here. Suppose the input resistance very small, this is a typical case compared to the output resistance. What is loading effect? We know there will be a very large loading effect. That is what we are finding out now. That is EO by EO dash is equal to 1 over 1 plus 120 ZO by ZI is 26. Now this works out to be 0.188. That means EO will be in terms of percentage, this is equal to 18.8%, or say if it is 20, if you take EO will be 20% or 1/5 of the EO dash. If it is 20%, 1/5. So EO will be 1/5 of the theoretical value. Suppose the EO dash is going to be 5 volt, and what we get in this instrumentation is only 1 volt. 4 volt is lost by loading effect. So heavy loading effect is there since the input instrument has got very low resistance. So we normally say such instrumentation should not be there, but here there is a special property. Since the resistance is a constant one, 26 ohm is constant, we are going to always get 1/5 of the voltage, which is constant ratio. Once we know the constant ratio, where the instrument is going to show 1 volt, write it as 5 volt. What is the problem? That is called the calibration process. By the process of calibration, we can write this 1 volt output from this instrumentation, that is from the oscillograph, write it as 5 volt, or 2 volt as 10 volt, like that. So the constant loading effect can be compensated at the time of calibration. This is possible. But if you don't do the calibration, we say there is error. If you do the calibration, the error is removed. Since it is a constant error, we can always remove it by the process of calibration. So in the absence of calibration, you have to say the error is there, but once you calibrate it, there is no error. But is it possible, if the loading effect is varying, whether it is possible to eliminate this error? That is not possible. That is what is demonstrated in the second problem. Second problem illustrates that loading effect in an instrumentation where the output is going to vary, that is our typical potentiometer transducer, you cannot compensate. That is not possible. We will see it. Now we are going to see in a typical measurements where this loading effect cannot be compensated. Now we have already seen for a potentiometer transducer, the output resistance of the potentiometer circuits varies as the displacement varies, input displacement varies, that output resistance also is varying. In that case, the loading effect is going to vary. That what we learned there qualitatively, but now we are going to see quantitatively. Now RO is, that is the displacement is moved within the potentiometer between points A and B. but at the point A it is 5000, at the point B for example 10,000 ohm. Here you are not asked to find out the RO, the problem here itself given, the values are given. And the instrumentation is two type of instrumentation. One instrumentation oscilloscope, with that it is again as in the previous case, and the second instrumentation is use the oscillograph of this to record the output voltage. Now how what is the loading effect in these two instrumentations separately? If you see, take the first case, oscilloscope, the loading effect, because ROE has got two extremes, the loading effect also is varying between the two extremes. Now that is RO1, this is RO1, we call it RO2 in two instances. So now you take the that is instrumentation A, for A, EO by EO dash is equal to 1 over 1 plus Z over RO is now say 5000, and then RA is 1 into 10 to the power 6. Yeah. So this is about 0.995. In the second case, that is the next extreme one, this is RO1, next extreme case is 1 over 1 plus 10,000. Other extreme case of RO is 1 over 10,000, same instrumentation is equal to, it is approximately equal to 0.990. Now here we have to learn one point. Since the input impedance is of the order of 1 mega ohm and the output resistance is few thousands of ohm only, though loading effect is varying, but it is near about 1 only. Loading effect is the ratio is near about 1. That means EO will be very near to the EO dash. It is because the input impedance is very, very large. So 10 to the power 6, so 10 to the power 100 times. We want only 10 times more only, but here it is 100 times and more. So when the input resistance is more than 100 times or something like that, then you will find, though it is varying loading effect, but the actual output voltage is near about the actual theoretical voltage, because loading effect is become very negligible, though varying. What is varying? Only third decimal it is varying. It is because the input resistance too large, very large compared with the output resistance of the potentiometer transducer. But when the input resistance is small, this varying output resistance, the effect is magnified. That is the case now. That is instrumentation B says EO by EO dash is equal to 1 over 1 plus, first case is RO is 5000. When the point is at the displacement is at point A in potentiometer transducer, divided by, this is 26. Now it is only 26 ohm. Now it is smaller in the input resistance. We expect to be 10 times larger than the output resistance, but here it is much smaller. It is just opposite effect. So this gives rise to very high attenuation, and it is around 0.005. That is equal to 0.5%. So if the theoretical voltage is 100 volt, the EO is going to be 0.5 volt. That is a high reduction of the actual value when compared with the theoretical value. So highly attenuated, nearly 0. Similarly, we find EO by EO dash for the other one, EO by EO dash for the other point of operation in the potentiometer transducer is 1 over 10 to the power of 10,000, okay, by 26. This is around 0.0026, 0.0026. So this also, if it is 0.2%, that is for 100 theoretical voltage, 100 volt, the voltage output will be only 0.2 volt. Previously it was 0.5 volt for 100 volt theoretical value. It is 0.2, still much reduced. So you find when the input resistance of the instrument is very, very small compared to the output resistance, the loading effect is enormous, and not only enormous, it is varying with wide limits. The 0.05 is around nearly twice this value. Previously you find it's near about 1, both of them near about 1 of the same magnitude, but here in this case 1 is half the other value, this is half this other value. So the loading effect is very large and varies wildly. So this is situation, and it cannot be compensated. This cannot be compensated by calibration. So we have to adopt some other method of avoiding loading effect, and for that the clue is obtained from the first instance. When we connect to this varying output voltage a very high input impedance, then this varying effect is not found in the output of the high resistance device. That is what you have learned, and that is to make use of this, what is done is, so we draw this again, the potentiometer transducer with its excitation voltage. This is your output terminals. This is our xi, input distance is given here. We have got the output voltage. Instead of reading through oscillograph, where the loading effect is varying and with and also void limits, instead of connecting oscillograph, you connect a device which will have a high input impedance, just like oscilloscope, but that it's a different one. We want to make use of here oscillograph. So naturally, the what we have got is power amplifier. We have learnt already. Power amplifier is a device which has got a very high input impedance. With very high input impedance, the output voltage is not going to vary widely as in this case of oscillograph. Now we know this output impedance of power amplifier is a small one. This may be of the order of 100 ohm. Now to this you connect your oscillograph. It is now 26 ohm. It's 1/4. But you find the 100 is constant and 26 is constant. So you find loading effect, even though there is loading effect, as our first problem, it is a constant value. So this can be easily be calibrated. Since loading effect is constant between these two instruments, it can be calibrated, and the effect of and this attenuated value can be written as the theoretical value, as we have done in the earlier case. So this is a solution for instrumentation. For that instrumentation where we have got a very high loading effect and varying void limits. So that is all regarding the loading effect and its instrumentation in measurements, in mechanical measurements. Next we are going to see how to make use of the 4-quadrant diagram. We already learned 4-quadrant diagram, where the different error sources within the instrument are identified by drawing the signal flow diagram, and find the total effect of the error source on the input signal. And that total error is from the total error we obtain a suitable least count, and that is what you are going to use it when we manufacture the instrument. That is a design problem. How to decide the least count of an proposed instrument. For this we take this same conventional example what we are seeing from the very beginning, a piston and cylinder type pressure gauge. Yeah, that is the say third problem, piston and cylinder type pressure gauge. The given values are, it looks like this. The diagram is like this. We got the spring to convert the force to displacement, and instead of pointer mechanism directly connecting here, we have a rack and pinion mechanism. This is a little different, and you can draw the rack on the other side, rack, and then a pinion. Now for this motion, so it will rotate in this direction. So you got pointer and this scale. This is called rack and pinion mechanism. Rack and pinion mechanism. Instead of simple lever mechanism, we use at the end of the piston rod rack and pinion mechanism. So the P is our input signal Xi. So we will draw the, as we are told, for drawing the 4-quadrant diagram, we should represent the whole instrument in 3 blocks. So first one is our piston area. This is our piston area A, Xi, that is our pressure, and from here we have got force, and force 2 we have got displacement d1. This is d1, and d1 is converted into, by using this rack and pinion mechanism, we convert it into beta, that is beta rotation, beta. Yeah, this is the instrumentation. And again we draw the signal relation for each block. This is our 1 by Cs, the spring. So first equation is F is equal to P into A. This is equation 1. for second block, D1 is equal to F by Cs. This is second signal relation for the second quadrant, D1, and then beta is equal to pinion, if you call pinion radius R beta is equal to D1, R into, so D1 is equal to, so that is D1 is equal to R into beta. So beta is equal to D1 by R. So here you will have 1 by R as the gain. So beta is equal to D1 by R. These are the three signal relations, and which we are going to represent in a just 1 minute. In a signal flow, in a 4-quadrant diagram. But instead of going for 4-quadrant diagram, we can all, since it's a purely linear instruments, we can analytically compute the values. Now what is asked in this problem is, find out A, find out A radius of the pinion R is equal to how much, and then B for a total friction, that is delta F. F is the force, and friction force FF is equal to, friction force is 5 Newton, friction force is 5 Newton, and then backlash. In the rack and pinion machine, we have got the backlash, we call it delta D1, backlash is equal to 0.3 millimeter, backlash is equal to 0.3 millimeter. So these are the error sources within the instrument, because we know F friction force is there, displacement is there. For force, friction is error, and for displacement, backlash is error, which we have learnt already. So these are the two error sources, and how to how much should be the least count, that is our problem. So before that, the radius of pinion is to be found out. The given data are the pressure P varies, P, that is the pressure varies between 0 to 1 megapascal, 0 to 1 megapascal. That is data, one of the data. The beta maximum is equal to 180, beta maximum is 80 degree, that is beta maximum angular rotation is 80 degree, and the piston diameter, piston diameter, this I will call it capital D, piston diameter D is equal to 20 millimeter. So these are the given data, and the spring constant CS is equal to 12.56 Newton per millimeter. So that is the given values of the this instrumentation, and the error sources are given. Now we are asked to find out what is the total error in terms of input signal, and then what should be the least count. Now to go to obtain that, we use the maximum values. P maximum is known, 1 megapascal, beta maximum is known, and area is known, since piston diameter is given, so area is known. So for a P maximum of 1 megapascal, what should be the F maximum? We can find out from this equation. So F maximum, if you find out, it is around 314 Newton, you can get it. Once F maximum is there, and D1 maximum you can obtain, because CS is given. So D1 maximum is equal to F maximum by CS, and that is equal to 25 into 10 to the power of -3 meter. So to say 25 millimeter. So D1 maximum is known, beta maximum already given as 80 degree in terms of, we convert in terms of radians, then R is known. So R is equal to, by using this equation, D1 is known and beta maximum is given, so R is equal to, we have to obtain as 17.9 millimeter. That is one of the missing data you can find out by using this signal relation of the individual block. Yeah. Once you found out this, later on now you can find out the total error in the input signal, that will be, that is, I'll just rub it off. Total error. Now delta P1, by again we have to find out this by using these signal relations. See, delta F is given, that the friction force is given. From the friction force we can obtain the delta P. So delta P1, if you call delta P1 into A is equal to our delta F or FF. This is equal to now area is found out, and delta F is given as 5 Newton, that is friction force. So delta P1, if you find out by using the given values, delta P1 is equal to 1.59 into 10 to the power of minus 10 to the power of 4 Pascal. That is a friction of 5 Newton. A friction of 5 Newton is equal to a pressure of 1.59 or 1.59 or 0.15 atmospheric pressure. Being 1 atmosphere is 10 to the power of 5 Pascal. So the error in the input signal will be 0.159 bar, around that. That will be the error due to the friction force. Now the error is, next error is given is in terms of delta D1. Delta D1 is given, delta CS is known. We find out what is the delta F for this delta D1. Once delta F is known due to this delta D1, and we can find out what is delta P2. So because area is given, so that is how we find delta P2. So delta D1, so if we find out, delta P2 comes about 3.768 Newton. No, delta P2 that is the force equivalent. Now the delta P2 equivalent is 1.2 into 10 to the power of 4 Pascal. That is an error of that is the error of 0.3 millimeter. That is when the backlash is 0.3 millimeter, that 3.3 millimeter is equal to 0.12 bar, approximately 0.12 bar in terms of the input pressure. So the total error in the input signal due to both the friction as well as the backlash is equal to addition of these two things. So you find 9, 7, so 2.79 into 10 to the power of 4. So we know when we draw the signal for when we drew the 4 quadrant diagram, we have to add this effect, because we have to overcome this first, and further this has to move to overcome the backlash. So it is additional, all the error is additional. So 2.79 or 2.8 Pascal. But this is the error in input signal. Now to decide how to decide the least count, can you put the same thing as least count? That is not allowed. Least count always in terms of units 1, 2, 5, and on multiples 10, 20, 50, 100, 100 or thousands, or 0.1, 0.01. See, these are the numbers normally used for least count. This you might have noted in usage of instrumentations. So what is the number which is nearer to this number? Because the least count should be the error, the least count should be equal to or larger. It can be larger than error. So to which number is larger than this? So only you have got 5. So now least count, take it as least count is equal to next larger number is 5. So because 3 is not used for least count. So 5 into 10 to the power of 4 Pascal, that is equal to approximately 0.5 bar, because 1 bar is equal to 10 to the power of 5 Pascal. So 0.5 bar instruments are there. So for this instrument least count should be 0.5 bar. That is what you have decided. If you decided this like this least count, and then the what should be the graduation length, that is another aspect, it should be 1.5 mm. If it is 1.5 mm and if L is the length of the pointer, then you know we should know what should be the length L for this least count. So for that, if you find out, it comes, you can calculate it, and that all R is equal to, we know for this error of for this if you consider this delta P as 0.5 bar, for 0.5 bar what should be the rotation beta, you can get it. Yeah, you can get for the whole instrument the gain. From the gain we know for the 0.5 input pressure what should be beta, then L into delta beta is equal to our length. So L it is coming about 21.4 millimeter. Yeah, converting this LC in terms of beta, we can, that is output angle, we can calculate this L. Yeah, this we can cross.